Okay, early morning hustle. It might not be morning for you, but it is early for me. So here, what we're going to do is the remaining 6 or 5 methods. The new way of doing some of these, like the old way, it works perfectly. The new way is interesting. So without further ado, let's begin. All right, so one way ANOVA. So this one has one explanatory variable and one response. I didn't highlight that in the last couple of videos, but you can think through that on your own. And so here what we would want to do is, colloquially speaking, do the different species of penguins have different average body masses. We have to remember that the 3 different species are here in terms of a statistical question. What we're trying to determine is there a significant difference in the population mean of body mass across 3 different species. Okay, so one way ANOVA is good for that because it's used to determine if 3 or more means if the means are the same. And so summarizing this, the only thing that's different from one population means is now we're looking at group by. Well, we technically did that last time too. So here are the means, standard deviations, the sample sizes, and different species. Okay, so visually speaking, I decided to do a violin plot this time. I'm providing the mean as a point there, and this should look very similar to us. Okay, it works. Okay, so boom, boom, boom. So obviously Gen 2 has a larger mean. So in terms of body mass, so the old math, I could do this with my eyes closed, at least I think. I would say ANOVA model. Okay. Oh wow, she's doing that again. Okay, sorry about that. Gotta get to my page anyway. But ANOVA, the way we do this in R is just specify AOV, and then what we'll do is provide the relationship is going to be body mass and G tilde species data is equal to penguins. Okay, and now when I run that, I need to summarize this with a summary function, not summarize. So I'm summarizing with a summary function. And so then here I get my mean squares between, mean squares within, and my test statistic and my p-value. Thus, we need to reject the null hypothesis. That's no surprise. No surprise. Now, the thing is, to get the ANOVA table, it takes a lot of work using this new mechanism, and I'm not gonna do that to you all. I'm just gonna show you how to get this test statistic. Okay. In other classes, I might maybe 305. You might do more with infer, where you would essentially do permutations, but that's not for this class. At least not for now. Okay, not this quarter. So we're going to specify, with using infer the relationship body mass. You can see that it's automatically filling in the variables because it's connected to the data frame, which is fine. Whereas before I had to type it out verbatim. The function I'm not going to use is calculate. So calculate and specify are used to, first of all, specify the relationship, and then I'm going to calculate the test statistic, which the ANOVA is coming from an F distribution. Okay. And so here we go. Here's the F distribution. Here's the test statistic. Okay. So that is model 6 ANOVA, and this is how you at least get the test statistic in the new way of working with things. Again, this is in a tibble or a data frame. We can actually concatenate, row bind multiple tests if we need to. Okay, so that's that in comparison. Now for simple linear regression. Okay, for simple linear regression. So simple linear regression is when you have two quantitative variables, both explanatory variable and response variable are quantitative. So does the flipper length predict its body mass? Is there a significant linear relationship between the flipper length and body mass? Okay. So this is me explaining the purpose for simple linear regression to see if there's a relationship, so you can use one variable to make predictions with another. Okay. Just because they're associated or linearly related doesn't mean that there's causality. Always have to say that. Okay. Just because they are linearly related doesn't mean that X causes Y. Okay. And so this is a little different in terms of summarizations. So we have the mean of the explanatory variable, mean of the response, standard deviation of the explanatory variables, standard deviation of the response, sample size and correlation. Because once you have all these numbers, you don't need the sample size. But once you have all these numbers, you can find the regression coefficients, the y-intercept and slope. So that's why I provided those numbers. Okay. Again, it says a tibble, aka a data frame. Okay. And then finally, we can create a visualization. Okay. So X and Y, G on point. We're going to actually smooth it out. And then this is nothing new here. The only thing really new here is this dash N. This means new line. So if I do that within the title, it's going to be our new line after length. So right here. We're gonna see this kind of in the next plot, but you can kind of see there's two groups here. And that goes back to, you kind of saw that in ANOVA, because this is I think Gen 2, and then these are the other two species. Okay, so there's obviously a linear relationship between these two. Okay? Alright, so then in terms of doing this in the old way, in terms of analysis, this is actually quite straightforward. It's very similar to one-way ANOVA, so I'm going to say SLR model. Okay. And then I'm going to say LM, so linear model, LM. I'm pretty sure those economic students they love LM. So this is going to be, how do I do this? Come on, Emmanuel, remember? Oh, yeah. So it's body mass, G, tilde, flipper length, I don't know the variable. Flipper length, MM. Boom, boom. Bam, comma, data is equal to penguin. That's not how you spell penguin. Summary, same thing. Summary, SLR model. Is it called penguins? Yes, it is. So I got my regression coefficient for slope, y-intercept, my standard deviation of residuals, my r-squared. All right. And so for this one, I'm actually going to oh, that's the old code. Okay, so we're good there. Okay. I got brain fart. The next thing you have to do is to create the tidy models. And I was wondering, why are there two chunks? Because those model metrics only come with other levels of code. I'm going to move my mic. That's how much programming I have to do right here. So the new method, I'm not trying to discourage you from using the new method. It's just a little bit more work. So here we have to first specify the model that we're implementing. Okay. We'll call it linear regression. No, I'm not calling this the function that we're using. Linear reg. Okay, we're going to pipe this into set engine. We have to specify the engine that's going to actually use to run the model, LM. Then we have to denote a workflow. Okay, it's to denote a workflow, model underscore workflow. Okay, and so workflow, and then I'm going to pipe this, and I'm going to give you an explanation on why they most likely made this more complicated. Add model. Okay, we're going to add the model that we specified earlier. And then we're going to add the formula. Now also the formula. Okay, where the formula is going to be what we set up here. I'm going to do a little bit of a copy and paste. Right here. Boom. Boom. And then I'm going to do model fit, and I'm going to pipe this, because if you look at this, nothing does with the data yet. Nothing does with the data. Okay, not model fit. Model workflow. Pipe this into fit, and data is equal to penguin. And then pipe this into pipe this into tidy. Okay. And I'm pretty sure I told you all, I think I might have to have you also run, I think Tidy Models has everything. If it doesn't work, I had to potentially have you include parsnip. I think that has fit. So if this doesn't work, I'm gonna have to do parsnip as well. Well, let's see. We're down all the way here. So here we go. Run this. Okay, it worked. Okay, good. So here's the y-intercept. Right, sorry. Here's the y-intercept. Here's the slope. Same numbers as above here. Okay. I know that was a lot, but the idea is you are able to do a bunch of models and have it output be a table, and it's easier to work with. That's why it's a little bit more complicated. What I'm going to do with this information, I'm going to call this model fit. Okay, pipe this here. But I'm going to now, because the thing is, when in this format, I don't necessarily get what I need for the metrics. But, so if I do this, I get my tidy fit. But if I do model, what does it look like? It looks kind of clunky. But there's some more information going on in the background that they're storing that you can't necessarily see. So if I do this now, model fit, and pipe this into augment, I swear this, maybe that's why I don't necessarily use it that much. New data is equal to penguins. So if you're doing a training model and this was your training, and then now you're doing a test, you can then supply those regression coefficients within that model. And then within metrics, and then this is the truth, body, mass, G, the response variable, and then you do estimate is equal to dot pred. So this is the predictions. And then this is my root mean squared error. It's going to be a little bit off from this value, just a tad bit off. Different estimation errors. And then this is my R squared, 0.75. And then this is another statistic that they provide. So that's a lot for this video. I think I'm already at maybe 14 minutes. But we're going to do multiple linear regression. And I think I'm just going to provide the key for logistic regression and not necessarily do that one. Just provide the answers in there just so you can have it. But, or maybe I'll just discuss it, but I won't necessarily go through the analysis of it. Okay. All right. Well, thank you and have a good day.